All right, new section today, inferences from two samples. We're doing two variances or standard deviations. We've already done in this chapter, we've done two proportions, we've done two means with independence, two means that were matched pairs, and now we're going two variances for standard deviations. So here we go. Key concept for this section, it's going to present the F-test, which is a new test for us for comparing two population variances or standard deviations. We introduced the F distribution, which is used for the F-test, a bunch of Fs. Know that the F-test is very sensitive to departures from normal distributions. It must be a fairly normal, pretty close to normal distribution in order to use the F-test. All right, here we go. F-test is hypothesis test. Here we go. Notation. This is huge. This is a very important slide. Your S1, N1, and maybe sigma 1, but these are S squared. These are all variances, but the first one must be the larger of the two variances from the samples. The must be the larger one is S1, S2 being the smaller. That means N1 is the sample size from the larger variance, not the larger sample size, but from the sample with a larger variance. And the population, this is the variance of the population because it's baby sigma squared. It also comes from the larger variance from the sample. Make sure you got those. All right, requirements for this to work. The two populations must be independent. That's going to happen pretty much all the time. The two samples are simple random samples. I mean, what a shock there. And number three, the populations are each normally distributed. Very strict requirement. They must be very close to normal. We can either use histograms or a QQ plot to see if they are normal or not, but they need to be very close to normal. A test stat. Here's our test stat. Very simple one. The test stat for F is just the variance of the sample, but the larger variance over the smaller variance. Remember, larger is S1, smaller is S2. Our p-values we get from technology. Critical values we're also going to get from technology, but there is a table. There's an F-value table to get your critical value, but we're not going to do that. We're going to use technology to find that. But that's the most simple test stat we've had yet. All right, properties of the F distribution when you see it. First of all, it's not symmetric. To be honest, it's skewed right, and you'll see a picture in just a second. The values of the F distribution cannot be negative. Everything's positive. And the exact shape, it's going to change shape somewhat, but it depends on what the degrees of freedom are. And there's 2 degrees of freedom based on your numerator and denominator, both ends, -1. All right, here's a picture of the F distribution and finding critical F values. So just like we've always done, your alpha, your sig levels over here. Remember, non-negatives, it starts at 0 and goes up to there. The value of our test stat, remember, is S, is the variance, the larger variance over the smaller variance. And that's where I guess we would find it right there. Okay, if two populations have equal variances, then your test stat is going to be close to 1. Think about it. If the populations have equal variances, their samples are going to have close to equal. And if the numerator and denominator in a fraction are very close to each other, that fraction is going to be very close to 1. So the better, by the way, our whole during this section is going to be that our two population variances are equal to each other. And the better chance of them being equal is when this right here is very close to 1. The closer our test stat is to 1, the better chance that is to being the case, because that means they're close. These can only be close if it's close to 1. Hope that makes some sense. That needs to make sense. All right. Consequently, if we get, I just said this, if we get an F stat that's near 1, it'll be evidence in favor of our null hypothesis that the two variances of the populations are equal to each other. However, a large value of F will be evidence against the fact that they're equal and probably lead to rejecting the HO. All right, let's do one example and we're going to be done. It says the same example we've done in the whole chapter. Subjects with the red background were asked to think of creative uses for a brick, while other subjects were given the same task with the blue background. Creativity score sponsors were scored by panel of judges. Test the claim that those tests with the red have creativity scores with the standard deviation equal to the standard deviation for those tests with the blue. So we're definitely testing the standard deviation. And the claim is that they're equal. Don't forget that. The claim is that they're equal, so the claim is going to be our HO. All right, and here's what we're using right there. There's our our variance from, actually it's our standard deviation. It's our standard deviation from our samples. So this one is going to be S1, that one's going to be S2. All right, requirement. Check your requirements. The two populations are independent. Check. Given that the design was carefully planned, we assume there for two random samples. Check. We don't have a knowledge of distribution, but we proceed because we've already seen this one before. So we're just going to assume it is from a normally distributed population. All right, here's the claim. We already talked about that. Our claim was that they were equal. The population standard deviations were equal, which means if it's false, that's our HO and our HA, our HO and our HA, that they're equal, not equal. So next thing, there's our sig level was 0.05. That's always important. And because we're talking about two population variances, we use the F distribution, which is right here. I just squared both standard deviations from the sample, and I got 2.3706. My degrees of freedom for the numerator, 35 minus 1. Numerator, 36 minus 1. I got those from the table that you saw earlier. So 2.3706, pretty kind of close to 1. Not real bad. We'll see how close it needs to be for this sig level, see if it's true or not. Okay, for the table, find a critical, we're going to use the technology, and we found the F value is this. This is the critical value. That's your critical value, and this is our P value, 0.0129. Remember, our alpha, our sig level we were using was 0.05. So our P is lower, which you know what that means. And also this number right here, I think if I remember correctly from the last slide, I think our F stat was like 2 point something. So that's not quite there. So here's what we're going to do. Step 7, since the P value is lower than the sig level, we can reject the null. Also, here's where our test stat was. Our test stat was 2.3706, and our critical value is right here, so it does fall in the rejection zone for sure. And because it falls in the rejection zone, just like always, we reject HO. All right, so there is sufficient evidence to warrant rejection of the claim because HO was the claim that the two standard deviations are equal. So the variation among creativity scores with the red background appears to be different from variation with the blue background because we rejected the claim that they were the same. And if we reject that claim, we're saying, okay, they're probably not the same. So the variation is different in that case. So hope that made some sense. I hope it's in a pattern. Man, this whole chapter we've been going, the same kind of deals, different tests for different things. But between the proportions and the mu's and now standard deviations, different tests, but we're really doing the same type hypothesis test over and over again. And I'll see you in class tomorrow and we'll work on it.